we were looking at search engine optimization. We're going to return to search engine optimization in due course, but I wanted us to start having a look at images and how images work and preparing images for the web, and also so that you have all the information you need to make progress on your assignment too. So hopefully by the end of today even, because we have 2 classes today, we might get the bulk of that done. Next week we'll be looking at, I think we'll take another, maybe a 3rd class, but we'll see how we go. Now, the first thing we're going to look at is how we would take, say, a black and white photograph and then store that in the computer. And much of the important stuff applies equally to color images and black and white images, but conceptually black and white images are just that bit simpler. Okay? So, let's say we have a black and white image and we want to digitize it. We often use the term digital synonymously with, super mega high quality, and that's incorrect. Something is stored digitally, it's just represented numerically. It doesn't mean it's high quality. So we hear about digital audio and digital video. I mean, YouTube is digital video. I don't think anyone would argue that's, high quality. The thing about something that is stored numerically, though, that is represented using numbers, that's stored digitally, is that you can make a perfect copy of it. You can just, copy the numbers and you have a perfect copy, which isn't something that happens with other kinds of storage systems. Now, so let's say this is the image that we want to represent digitally. With when you want to digitize something, when you want to digitize an image, you break up the image into non-overlapping rectangles. Usually they're squares. They don't have to be squares. I think mine were squares, and then I changed them wider. They can be rectangles. Okay? And then we look at each individual space, each individual area, and we get the average darkness of it. So this light one here on average is that. This black one here on average is black. This here is kind of, I don't know, that looks maybe like 80% white and kind of 20% pure black. So on average that might work out to be kind of, I don't know, 60% white kind of, perhaps. One of these quantization levels, they're called. And this is an important point. So when we look at any one of these rectangles here and we get the average lightness and darkness of it, that will have, kind of infinite precision almost. We then slap that into one of these ranges. We call them quantization levels. And so anything that's between this shade of grey and this shade of grey we'll call 7. Anything between this shade of grey and this shade of grey we'll call 0. Anything brighter than this we'll call 15. Anything between here and here we'll call whatever. So just putting them into ranges. And in fact, the number of quantization levels would have a huge impact on the quality of the digital representation. So it's a bit like I wanted to record your heights. And so I got you each to line up against the wall there, and I counted how many bricks you were. So some of you might be some of you might be like 1, 2, 3, 4, 5, 6, 7 bricks tall. Some of you might be 8 bricks tall. Some of you might be, isn't much. Those bricks are quite big. I'd say there wouldn't be much of a difference between all of you. Okay? However, if we were in a different room with tinier bricks, if we were in a room with much smaller bricks, and I was to measure your height in bricks, it would be a much more precise measurement. Saying someone is 7 B219 bricks tall gives you some information. It tells you, they're between this height and this height. If there was some room X123 that had, much smaller bricks, I'd say, well, that person is, 25 of those bricks tall. That's a much more precise measurement. So we take the level of grayness and then we figure out into which one of these ranges it fits. For black and white images, typically 256 quantization levels, 256 shades of grey is loads. It's plenty. Now, so digital images then are made up of rectangles called pixels. A lot of people, they used to be called pels as well. You don't see that so much anymore. So pels for picture element or pixel, picture element. And so each pixel has one color. It's only one color. And it represents the average color. Like its color is the average color of the part of the picture that it's representing. So, this one here is standing for all of that part of the image. Now, so the more pixels you have then to store the image, the better the quality is going to be. And you hear people talk about dots per inch, DPI. Even in the metric world. And do you use DPI in France? Have you seen that on, no? Not sure. So if you get a printer or something, it'll talk about DPI, or a scanner, use DPI. And that's dots per inch. And so you might, if you're scanning, if I had a photograph or document and I was putting it into a scanner to scan it, if I had, 800 pixels by 800 pixels, that's quite a lot of pixels in an inch. You could also scan it at 300 pixels by 300 pixels. Now, depending on what you're going to do with it, it might be fine or it might not. If you have a picture scanned, if you have an A4 picture and you scan it at 300 DPI and you put it on your Facebook page, it's going to look fine. If you were to print it into a poster, you'd start to see the pixels. It wouldn't look good. And so, depending on where the image is going to go, it's important that you have enough pixels to make it look good. You often see it in a lot of places, in shopping centres and stuff. Someone takes an image off the web and organises it maybe in PowerPoint or something, and then sends it off to the printer, and it comes back as a huge poster, and it looks like it's crap because images for the web aren't designed to be used in posters. Now, so here I have an image at 600 pixels by 400 pixels, and it looks fine. Actually, if I was to print this out on A4 at 600 by 400, it wouldn't look that good at all. But on this screen, it's fine just because of the resolution of the screen. We have higher expectations of printed documents. Well, actually, maybe I'm old. I have higher expectations of printed documents. Maybe you've no expectations of printed documents. At 300 pixels by 200 pixels, it's starting to give way on my screen. Can you start to see, starting to go there? Now, it's important to realize too that if you go from 600 pixels by 400 pixels to 300 pixels by 200 pixels, there isn't half the information in there. There's a quarter of the information because you've halved it in both dimensions. So this would be a quarter of the size of the one we just saw. At 150 pixels by 100 pixels, it's definitely starting to give. You can see the pixels there. And then at 70 by 50, it's not much use. You could even see that there are actually 50 pixels. We could count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's about a fifth of the way up, isn't it? So you can actually see each and every one of those individual pixels. Now, of course, you don't want to see pixels. You want the illusion of, continuous image. And so you need enough pixels to pull that off. But when people start working with digital images first, that's the thing they find hardest to get to grips with. Especially if If they're scanning it in one size, then they see it on the screen and they're going printing it another size, you need to bear in mind that's how many pixels you have is what counts. Now, the more bits you use per pixel then, the better the quality as well. And this goes back to the quantization levels. So the more quantization levels you have, the more accurate the representation is going to be also. So here we have an image with 8 bits per pixel. So there are scope here for 256 different colors. Now looking at this image, I don't think it's used all 256. Like the whitest white there isn't that white, you know, the brightest color isn't that white, and even the darkest color isn't that black. So this image I don't think has used all 256. Excuse me. If we go down to 5 bits per pixel, so there's only 32 different shades of grey in this image, would that be right? 2 to the power of 5 is 32. So this image only has 32 shades of grey instead of 256. And to be honest, it looks fine. So if you were on your halls and you were posting this to your Facebook page and you had to pay lots of roaming, sending this image might cost 80 cents. But sending this one would only cost 50 cents. I think the 50 cent one is a very good value for money. The 80 cent one is bad value for money. And this is the kind of thing you're interested in when you're preparing images for a web page. You don't need to have maximum quality. Like the maximum quality setting probably represents bad value. It's probably 2 or 3 times the size it needs to be. Certainly this one here is perfectly fine. This one here only uses 4 bits per pixel, and so there's only 16 different shades of grey in here. We could nearly count them. Now, did anybody notice that start to go? It's hard to see. I think you don't see where it starts until you actually, if you look at the 3 bits per pixel, it's only 8 different shades of grey. You start to see up here now, this is where it's starting to give way first. So what's happening is a value that might have been a value that might have been 30% grey is now being bunched in a range. If you'd 8, might be in a range then from, I don't know, something like 25 to 37. So the ranges are getting bigger. So each pixel then is being forced to its closest match. It's, you know, it's representative, and so it starts to get a bit ropey. Now you know where it starts, where you first start to see the problem. You can actually see it now, I think, when you go from 5 to 4. We might not have seen it before. You can start to see it now up there. So we go to 3 bits per pixel then. There's only 8 different shades of grey. We could nearly count them. Oops. There's a darkish one. Well, 1, 2, 3, 4. And then the white ones there, it's harder. We go to 2 bits per pixel. There are only 4 shades of grey. Dark, not so dark, not so dark, and quite light. So every pixel now in this image is being forced into one of 4 slots. So a pixel that was 10% grey is now being represented. There's now like a range from 0 to 25, and say 13 is being used to represent all of those. So something that was 0 is now forced to 13. Something that was 24 is now forced to 13. Something that was 12 being forced to 13 isn't such a big deal. But so we get to see this banding here. So some continuous, you know, shades of grey that vary in a gradient, they're that's gone now. It's just like you're this color, you're this color, this color, this color, pick one. And so it's like if we had very big bricks, you know, you're height 1, height 2, height 3, or height 4. You're only one of those 4 heights. And that's quite a crude measure. Whereas if you had, you know, 32 bricks on the wall, between 0 and 2 meters, you could be a bit finer. So we get the idea. Now there are 2 dimensions here. You have 2 bits, 2 different colors with 1 bit. There's the number of pixels per space, you know, per inch, whatever. And there's the number of bits used for each pixel. And that's something we see again and again in digitization. You have the sample rate, which is how often you have a look at something. So how densely packed together are the samples. And then there's the precision of each sample. To use, you know, have you 16 ranges, 256 quantization levels, 32. So it's the same, for example, with audio. With audio, you have 2 things going on. You have a sample rate, where you might have 22 kilohertz or 44 kilohertz. That's how often you look at the sample. And then you also have the precision of each sample, which would be the number of bits per sample. And we typically go for 8 bits or 16 bits with audio. And it's very instructive to take some audio, you know, 10 seconds of a song or a piece of music, and to resample it with different sample rates and different bits per sample, and see how you hear the difference. So with the when you lower the sample rate, you start to get kind of hissing. But when you lower the when you reduce the number of bits per sample, it starts to get really muffled. You know, and it's interesting to do that. But when it comes to digitization, those are the 2 things. It's how often you take your sample, and then how precise each sample is. So there's two things going on at one time. And that can be tricky to manage in terms of conceptualizing what's going on. What we're going to look at now is we're going to bring color into the mix. And I believe I might have done some of this with you earlier in the semester, just for the crack. So, well, not this semester, last semester even. Now, when it comes to expressing levels of grey and putting numbers on that, that's quite an easy thing to do, because, you know, we have ranges from black to white through grey. And that's easy enough to visualize and conceptualize. So if, for example, I had 20 grey shirts on a rack there, and, you know, I said I wanted some ordnung, you know, it would be very easy to organize my shirts in order. From, you could black one at one end, white ones at the other, and then just the different shades of grey along the way. And that'd be easy enough to do. Color is not so organizable. Like, we know green isn't the same as blue, but I mean, is green more something than blue? I mean, this, you know, the second from the right shade of grey there is more light than, you know, the second from the left. So one is more light than the other. But I mean, is green more what than blue? I mean, it's more green, but like, how do we put numbers on color? So if I had all of my shirts on a rack there and said organize them for me in order, that wouldn't be so easy. I even brought a load of color chips, but I'm not going to use them. So how does that work then? That's the problem. How do we sort color? How do we organize color? How do we put numbers on color? And that's not an easy thing to do. There are a couple of different ways to do that. And the most natural way, the most natural system for describing colors is the hue, saturation, and brightness system. And that uses 3 different variables. The first thing we need to realize about light and vision and color is that the stuff we see with our eyes is the same stuff that's coming out of the 96 FM transmitter. It's the same stuff that's in your microwave. You know, we think of light as one thing and radio as another thing. And actually, no, they're all the same thing, which I find to be a complete head wreck, actually. Do you know? I can't get my head around that. But they are the same thing. But humans can see a small range of this electromagnetic spectrum. So with our eyes, we can see a bit of that. Different species might see different subsets of that range. Some might see a bit into the ultraviolet, some might see a bit into the infrared. Aliens from another planet might be able to sense completely different parts of that range. And Newton explained to us that, what did he explain actually? I mean, he explained the rainbow, but what was the point? Yeah. So I remember the experiment. I'm just saying, what was the point? What did it tell us? I'm not sure. But anyway, we have our rainbow, where we have, you know, red on one end, and orange and yellow and green and blue, and purple on the other. And the position that a color occupies in the rainbow is connected to its wavelength or its frequency. And humans can see from around kind of 720 nanometers to, I think, 390, kind of somewhere along that range there. Roughly anyway between 700 nanometers and 400 nanometers we can see. So here we have some colors all lined up for us nice and neat, even with numbers on them. So we can order colors by their wavelengths. So if I had a selection of shirts, each one of these colors, you could line them up fairly easily. So the wavelength of a color is a good way to start organizing them. And it's something we kind of we get it. We're used to rainbows. We get this organization of color. Now, of course, this is called the hue. And the hue then is connected to the wavelength. So where something sits on this rainbow scale, as we could call it, is the hue. Now, but there's more going on, of course, than just that. I mean, there's no pink in the rainbow, there's no white, there's no brown, there's no black, there's no grey. So there's a bit more going on there than just the hue. See, looking at all of these, we could quite happily say that these belong somewhere in the blue part of the spectrum. So in the blue part there, that's where they belong. But these are all different colors, but they all have the same hue. Here, all of these colors all have the same hue. They're all in the kind of yellowy part. All of these have the same hue. They're all down the purpley end. So there's more going on than just the hue. And it turns out that color can be diluted. So you can have very pure color, or you can have a diluted, faded color. So if we consider a cup of hot chocolate or a cup of coffee, if you pour milk into it, it gets a bit diluted. If you pour some more milk into it, it gets a bit more diluted. As you keep adding milk, it's still brown, but it gets paler. And that is known as the saturation. So if the saturation is high, then the color is very pure, very strong. and if the saturation is low, it's pale, it's faded. If you leave a picture in the windowsill in a place where there's sun, it's a bad example in Ireland really, but if you leave it there for 20 years then in Ireland and it starts to fade, it's the saturation is being pulled out of that. And if the saturation is turned off completely, you get a shade of grey. So if we look here, on the left, that green is very high saturation. And as we move right, the saturation is being turned down. So we have two things now. We have hue and we have saturation. So we could have green, and then we could reduce the saturation of it. We could also have blue and reduce the saturation of that. So the greenness and the blueness and the redness and the orangeness and the yellowness, that's the hue. And then the saturation then is how pure, how strong the color is. So here when we reduce the saturation, so I've kept everything the same here and just modified the saturation. And these here all have different levels of saturation. These all have different levels of saturation. All these different blues have different levels of saturation. But hue and saturation don't tell the full story. All these yellows here actually have the same hue and saturation. There's one more thing going on, and that's the brightness. Now we're on familiar territory here because this is a bit like organizing, black and white. You just, you've the bright one on one end and the dark one on the other, and you've all the intermediate shades in the middle, although they wouldn't be shades of grey as such. So another way to think of it is if you if you're nostalgic for the 90s or something and you want to get a coloured light bulb for your room, okay, you could go into B&Q maybe and they might have a whole range of different coloured light bulbs all organised by hue. So there's like the red ones, the orange ones, the yellow ones, green ones, blue ones, okay? Looking at them then, you might find that some of the red ones are pure red, but some of them are a bit pink. You can kind of see how pure the red is. There you're looking at the saturation. So you got your hue and your saturation, and you bring the light bulb home and you connect it up. And then you have a dimmer switch on your wall. And that's the last thing then. The dimmer switch then, you can adjust the brightness. And so when you have the brightness turned up full, your hue red, highly saturated light bulb will be up fully and would fill the room with red light. As you turn the dimmer switch down, it's still red, it's still saturated, there's just less of it until eventually you turn off the light switch altogether and there's no light at all and it's black. So you've hue, saturation and brightness, those three things working together, and with those three things you can pretty much specify any colour you want. You can also specify the difference between colours. So this man's cork gas shirt and this man's red hoodie, they're both red, okay? They both got the same hue. They both got quite strong colours, in fact. I mean, that's quite a strong red. That's also quite a strong red. Like it's not tending towards pink at all. It's red like. But the difference there is the brightness. This is a bright red and that's a dark red. Whereas if you take this man's top here, this strong blue, that's blue. His at the back there is also blue, right? Say hello. But this is a highly saturated, like they're both blue. There's no doubting their blueness. But the strong one here is a very highly saturated blue. Whereas the blue at the back, that's been diluted a bit. That's kind of a less saturated blue. And they're both quite bright. Now, so with hue, saturation and brightness then, you have three values that can give you an accurate description when combined. Typically, hue is expressed as a point on the radius of a circle. So we measure it in degrees. So you might have, 300 degrees, 270 degrees, 90 degrees, and that's how we express the hue. Saturation is usually a percentage, 100% strong color, 0% gray, and then the brightness, 100% bright, 0% black. Most operating systems would have some kind of color picker built in, so you could go into something like PowerPoint and try to add, mess with the colors. So if I go in here now, I can crank up the color picker. It looks slightly different in Mac OS, well, quite different from Mac OS to Windows. Unfortunately here, this is a very good one in Photoshop. Unfortunately, on this particular representation, it doesn't give you the numbers. But so, if I come out here, so here's the hue here, and you specify the hue by specifying, how many degrees you've gone around the circle. So if this was 0, this green here, this might be 90. If I go over here, if I just look here, just go into this view, is that actually 90 for hue? It's 2 degrees. Okay, so it starts here then. This is the 0 point, I guess. So this is probably the 270 or 290 up here, is it? Okay. So it seems to be spinning beach ball of death. How ironic. Okay, so this is 0, this is 90, this is 180 over here. But anyway, you measure it in degrees. Okay, so where you are around the circle tells you the hue. And you can see there we're going on a little rainbow trip. We're going red, orange, yellow, green, blue, indigo, violet. Very short there to get the two of them together. Okay, now. So here we have like hoodie number 1. Okay, as we reduce the saturation, it becomes paler. The color gets washed out a bit, and we get something like hoodie number 2 at the back. Okay. However, actually it's not a hoodie. My apologies. As we can also adjust the brightness then as well. So we can reduce the brightness, and obviously as the brightness comes all the way down, we end up then with something like black. You can also use sliders. Most applications would have sliders, so you can adjust the hue there. So here, look, the hue is basically your rainbow scale. Your saturation is, strong to washed out, and then your brightness is light to dark. And that's a good way to get a feel for how that works. So you can do that in Photoshop or even in PowerPoint. It works perfectly fine. I do want to press on a little bit just because I felt like we made a late start. So that's the hue, saturation and brightness model. However, there's more. There's the Rgb system, which is the one we're most interested in. So you might remember from physics class this notion of shining a red light, a green light, and a blue light onto the same space. And where they all overlap, you get white light. Where the red and the green overlap, you get yellow, which is quite counterintuitive, I think. And where the red and the blue overlap, you get magenta. And where my physics class, red, green, blue, yellow, magenta, turquoise. No. So, with the Rgb system, we have 3 values again. And the first one, red, represents how much red is in the color. The second one then, green, tells us how much green is in the color. And the blue one tells us how much blue is in there. And these three values combined tell us what the colour is. So this man's shirt here up the front, the gas shirt, do you think the red value on that is high or low? How red is that? I can't think of an easier question. How red is this man's shirt? Very, very red. So it probably has a high red value. Okay, there we go. No. So the red value, green value, and blue values, they're represented, we usually range in a range 0 to 255. And we like to do that just because that's 8 bits. So when you hear like 24-bit color, that's because it's got 8 bits for red, 8 bits for green, and 8 bits for blue. So there was a time when phones were so bad they boasted about how many colors the screen could do. Do you know? God bless the 3210 and Snake. And, you know, things haven't been the same since, really. Now, actually, that would be a great app, a Nokia 3210 simulator for your iPhone. So you could play Snake and do things the old way. Now, anyway, I digress. So, if the red value is high, here it's turned up to maximum, the green is 0 and the blue is 0, then red is the only thing at work here. Red is the only color in play. And it's turned up fully, so this is pure red. Here, the red is 0, the green is 0, so there's no red, no green. And the blue is almost turned up to full. So this is quite strong blue. When you have the red turned up fully and the green turned up fully, and no blue, you get yellow. And here these are turned up to the maximum, so that's pure yellow. Here, there's no red and there's no blue. So there's only green at work here. But you notice that the green isn't turned up fully to 255. It's about halfway, I guess. And you can see that it's a darker shade of green. There's no doubting its greenness. You know, its greenness isn't in doubt, but it's not a bright green, it's a darker green. Here we've reduced the green value even more. And so now the red is 0, the blue is 0, and the green is only 96, and you can see it's a good bit darker. The RGB system is additive. The more things you add, the higher the values, the brighter things get. When the red and the green and the blue values are all the same, you get a shade of grey. Here the values are quite high, so it's at the bright end of the scale. Here, again, the red and the green and the blue are equal, but the values are lower, so it's not quite so bright. As we reduce the values further, it's still grey, but it gets darker. When the red value and the green value and the blue value are turned up to the maximum, you just get pure white. What's coming next, do you think? When the red value is 0, the green value is 0, the blue value is 0, you just get black. Now, you probably saw something like this in SOF 6007 when you were specifying colors in your style sheet. And you can say, actually in CSS, you can say you can say RGB open bracket and put in the RGB values one after the other. Or you can use the more common hash hexadecimal notation. So here, for example, this color, this blue here, has a red value of 128, a green value of 128, and a blue value of 255. The hexadecimal equivalent of 128 is 80. So you get 80, FF in this case. And we have the same going on here. In general, when an image is stored, you have a value for the red, like for each pixel you have the red value, the green value, and the blue value. And then for the next pixel you have the red value, the green value, and the blue value. it can be useful to look at the red channel, the green channel, and the blue channel separately. So Photoshop lets you do that, and you might want to just edit things in the red channel. The red value for a red color is quite high. If the color is red, the red value is high. If the color is white, the red value is also high. We saw that white has a high red value, high green value, and a high blue value. So in the red channel, the difference between red and white is actually quite hard to make out. So we can see here. Here in this representation, the red and the green and the blue are represented in black and white. And so where there's white in the red channel, that's a high red value, and where it's black, it's a low red value. And we can see here that in the red channel, the difference between red and white is hard to make out. Whereas in the green channel, it's quite easy. And in the blue channel, it's quite easy. Oh, obviously the difference between blue stripes, and if there are any, are there? No. In the green channel, are there any green? No green stripes either. No. You can imagine my delight when I saw 3 doors all lined up for me, red, green, and blue, one after the other. So obviously the red door in the red channel is the lightest. In the green channel, we notice that the green door has the brightest value, the highest values. And in the blue channel, go figure, the blue door has the higher values. So even though they're quite dark, the red and the green and the blue channel, we can see which is which. Just a quick game there, I guess. So here, the red value and the green value, so the first 2 digits of the red value, FF, the next 2 digits are the green value, and then the last 2 are the blue value. That gives us yellow. Red's turned up fully, green turned up fully, gives us yellow. And Chiza, what do you think this colour is? So there's a red value, a green value, and a blue value. Is the red value high or low? High. The green value is quite low, and the blue value is quite low as well. So in this colour, it's pretty much mostly red is all that's at work here. There's a little bit more going on, but those values are so low that I don't think it's going to take away from its redness. I'd say when we see this, it'll just be a shade of red. Yeah, that's red, no doubting that. Next up there, what do you think this is? So yeah, so the red isn't doing anything. There's no red here, there's no green here, there's only blue. So there's no doubting its blueness. Would you like to speculate as to what kind of blue? Yeah, I mean, it's certainly not, oh my God, Las Vegas blue. It's probably a darker blue. Now, I don't think it's navy blue either, but it could be quite dark, I'd say. Oh, that's quite dark, actually. Yeah, you're right. Okay. Next up there. Okay, it's a trickier one now. You're out of luck there. So there's a red and a green and a blue, and the blue value is the highest. So there's more blue at work here than anything else. But the red value and the green value are not trivial. They're quite high. They're very high, in fact. If the red and the green and the blue were equal, what would you have? Grey. Sorry, yeah, if they were all maximum, they'd be white. And they're not far off all maximum either, in fact. But if the red and the green and the blue were equal, you'd have a shade of grey. So I think we could look at this as a shade of grey where the blue edged ahead a bit. So this would strike me as, well, are those values high or low? I mean, are we at the, if there was a shade of grey, if they were all equal, if it was D0, 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 would that be the high end or the low end? Be the high end, so it'd be quite light. So this strikes me as shade of blue that's heading towards white. So I'd say it's a pale, pale blue. Hello? Yeah. And sure enough, that's what it is. Are we out of time? Okay. Great stuff. So guys, I'll see you in a minute.